Hi, this is 4829 heat transfer through clothing. Some of you have asked me a very, I think it's a very good question. So I thought I just spend a few minutes scribbling and making a point here. So this is the clothing part. So some of you have asked that since we have a boundary condition here that is a convective boundary condition minus k del t del x at x equal to 0 is equal to h times t at x equal to 0 minus t infinity, and then on this end we are saying that it should not have frostbite. So in other words, it is 0. So then the question that some of you had is, if we start with governing equation, del square t del x square equal to 0 because all other terms drop out, that with the two boundary conditions, this plus 2bc should be enough, to solve the problem. And so the confusion was, well, that seems to be enough to solve, but as you plug in numbers, it doesn't work out. I want you to be absolutely sure that this is correct. So we better redefine what we mean by we have solved the problem. The big trouble is this distance um, is what you are solving for. So this is unknown. So if this distance is L, so then the solution will have L in it. That is unknown. Sorry about that. That is unknown. So yes, you have solved the problem, but you have solved it algebraically. You cannot get numbers out of it. So it's not really co complete solution. And the trouble is that these other layers that are touching, they matter. They matter because um, the amount of heat transfer that is going to happen here, it depends on how much heat can come through this one, this one, this one, and so on, because it's the same heat that has to come through all of the layers. So we cannot just solve for these two layers when this clothing L is unknown. So another way to look at this problem, I think this problem is better done not this way, governing equation way, but using a resistance formulation at, at this layer. But if you just consider this layer, basically the solution to this is what I'm about to show. And so the solution would be minus k dt dx at x equal to 0 is equal to h times t at x equal to 0 minus t infinity. And so I can write this part as minus k minus k times, um, if this is my x direction, or maybe I should choose the x direction the other way. So then minus k dt dx would give me this, if I call this temperature as T star, so T star minus 0, that's in here, is divided by L, okay, it is equal to H times T star again, because T at x equal to 0 is T star, and minus T infinity. So this is what you'll get. So even if you come through the governing equation boundary condition way, this is basically what you're going to get as the solution. So the point I want to make is, in this one equation, the two unknowns are T star and L. You cannot solve for both. And so that's what will happen if we just stick to this one layer and try to do everything. We're going to keep running into this problem. And that's why the way to solve this problem is from other known data, like you have here, and you know temperatures between these 2 points, and you know the resistance. From that you can get the flux, and you equate the flux between these two resistances. This is one, resistance 2. You add them up, you know these two temperatures. So here it is -5 and here it is 0. So between those 2 points, you write the flow equation. But so the only unknown in these two, when you use these 2 points, is this L. Whereas on this side, everything is known. You can find the flow. So the flow is known, so you equate that with this side, then you solve for L. There's only one unknown. Okay, thank you.